Hey there, Math 2403. Welcome to unit number 5. Today we're going to talk about the central limit theorem. This is basically where we look at the distribution of sample means. And when we're discussing the distribution of sample means, we'll look at various measures such as the mean of the sample means, the standard error, and we'll even look at a way to sort of tweak the theoretical central limit theorem to be more applied to us using a new distribution called the student t distribution. So let's get right to it. Since unit 1, we've been collecting data and then doing numeric summaries. We calculate the mean of our sample set. Imagine a procedure where we collect a sample, calculate its mean, and then we repeat it. So let's take another sample, calculate its mean. A third sample, calculate its mean. And all these samples are coming from the same population. I'm creating a new data set where I have the mean of each of my samples. So I can start studying my new data set of means. Now these means will have a distribution, they'll have a center, and we'll be able to measure their spread. So we're basically doing a transformation from individuals to grouped data where we're studying sample means. When we do so, we'll end up with new attributes for the middle, the mean of my x bars, which is the mean of the sample means. And we'll also have a standard deviation of our sample means, measuring how spread out those means are. We'll call that the standard error, or the standard deviation of the sample means. So it's a fairly simple procedure here. I'll do a little example. I get a hold of 50 friends on Facebook and I say, hello friends, could you guys all send me your social insurance numbers? And 50 people all agree, but they're afraid, so they only send me the last 4 digits. It turns out the last 4 digits of your social insurance number are essentially random. The other ones have some meaning as to where you were born or when you were born, but the last 4 digits are basically random numbers. So my first friend there had a mean of, or had values 7272 for their last 4 digits. And then I had a friend whose digits were 2037 and another friend who was 4568. I took these values, essentially random numbers, between 0 and 9, and I made a frequency histogram for them. So I counted how many zeros there were in this group, how many ones, how many twos, and the results are given here. So there were like 24 zeros or 19 ones, etc. The shape of this distribution was pretty much what I expected to happen. With 200 digits, I kind of expected we'd end up with a uniform distribution. It's off by a little bit, just because I don't have a huge sample. If I had 2,000 digits or 2 million digits, I'd expect it to be, more closely uniform. After having these 200 digits, now I can do another experiment where I calculate the mean of each person's 4 digits. So person 1 had a mean of 4.5. Here's a person who had a mean of 6.5. So now I have a new data set. It only has 50 values in it. I made a frequency histogram of these 50 means. And you can see the results given here. So, most of them had a mean between 4 and 6. But no one had a mean of 9 and no one had a mean of 0. I mean, the only way to get a mean of 0 would be to have, all zeros. Actually, you could have 3 zeros and a 1, and maybe it would be rounded down and be in this category. But we're supposed to recognize something from, or learn something from this. We see that our original distribution or population is essentially a uniform distribution, but our x-bars have a pretty nice bell curve. Not really the way I drew it, but it's pretty good. And that's a neat thing that happens when you study the sample mean, is that the means tend to follow a bell curve, even if the data that they come from doesn't. So that's the neatest thing about sample means. And we can capitalize on that because we're experts at dealing with the normal distribution. Once we know we have a bell curve, we can convert to z-scores, and then we can calculate probabilities. Another thing we're supposed to take a look at here is, I have a mean for my original population, and then I have a mean for my sample, and they're in the same place. So the mean of my sample means is equal to the mean of the population. If we want to evaluate these things based on their standard deviation, and I don't know what it is, I didn't calculate it. The mean of the standard deviation of the first group is, I don't know. But I can see that just looking at the picture, that because they have the same scale on their x-axis, that this group is way less spread out than the original population it comes from. So the standard deviation of the means is smaller than the standard deviation of the population that it comes from. And in fact, it would be even smaller yet had we taken larger sample sizes. Imagine if we took groups, instead of looking at this in terms of groups of 4s, maybe if we looked at larger blocks and found the mean of these blocks, you would start to see less variation, because it'd be almost impossible to get values in these lower and upper categories, because the only way that it happens is if you have almost all zeros or almost all nines. So this is basically bringing us to this thing called the central limit theorem. We sort of have seen an example of this now. Here are a few more showing you the starting populations and then taking samples from them and calculating the mean. So in this first row here, the sample size, you can't really see it that well, is size 5. And then in the next row here, we have samples of size 50. And in the last row, we have samples of size 500 from these original populations. When you start with a uniform distribution for your population and take samples of size 5, you get a pretty decent bell curve. As you increase your sample size, you continue to get bell curves, they just aren't as spread out. Notice the scale is the same on all the graphs. That's why this last one doesn't really look like a bell curve. It's too zoomed. We'd have to zoom in to see it. We're too zoomed out. If you start with a normal population, yeah, of course you expect to see normal for your sample means, even when you have small samples. But when you have skewed distribution, say, then you'll see that this first one hasn't quite turned into a normal distribution yet. But as we get larger sample sizes, then we do. So as long as n is large enough, we can guarantee ourselves that we have bell curves. There's a neat little website you can play around with where you can draw your own distributions. Here's a normal distribution, and you can set the sample sizes that you'd like. I set mine to be 5 for this plot and 25 for the last one. If I start with a normal distribution and I take 10,000 samples, these are what the plots look like. If I start with a uniform distribution and I take 10,000 samples, you see that I even get a normal distribution even at 5, which is pretty small sample size. If I start with a skewed distribution, that's when things start to go, off the rails a little bit. If I do 10,000 samples, you'll see that, that when n equals 5 case that we have something that's still a bit skewed. But once we hit 25, things are good. The magic number we use in statistics is 30. As long as you have sample sizes that are 30 or more, you get yourself a bell curve. Even when you have different, weirdly shaped things, you can make custom distributions here. Suppose I want something, maybe, trimodal. And let's take samples from that. Even that turned out to be pretty good, even at the n equals 5 case. So by 30, it's really good. So this is a nice way to transform any data set basically into a normal distribution. We just don't study the individuals anymore. We study means instead of the individual scores. Here's the central limit theorem all summarized. The mean of the means equals the mean of the population. The standard error of the mean, I said, was smaller than that of the population. And the actual relationship is it's inversely proportional to the square root of n. So standard deviation of x bar is just sigma over root n. The coolest feature was that you can start with any population and you end up with means being normally distributed. And then to do your calculations, you'll need a new z-score. We have been using z as x minus mu over sigma. Well, now we're not studying individuals anymore. We're studying the mean. So we'll subtract the mean of the means and divide by the standard deviation of those means. And this piece can be replaced with the formula sigma over root n. And the mean of the means can be replaced with just mu because they're equal. So now we have this new formula for z. It may be a new formula, but it's still a z-score. So you interpret it the same way. A z-score of 4 is weird. A z-score of -1 isn't weird. A z-score of 0 means you're at the mean. So even though this is somewhat new, it's resting on a lot of the things that we've already done. Example here, we've been studying BCIT students for a while, and when they come to BCIT and they're male, they weigh 173.2 pounds. And their standard deviation is 29.5 pounds. I've been studying BCIT students long enough that I feel pretty good about using mu and sigma as population values. The weight of students tends to be normally distributed. So we have a bell curve to begin with. We can now answer some questions. I'm walking around campus. I, randomly grab a BCIT male student and I weigh them. What are the chances that they weigh more than 180 pounds? So let's let x be our variable, which is weight, and that variable is distributed normally. It has a bell curve, and we're saying that the mean is 173.2. And then we're asking the question, what are our chances of finding someone who is greater than 180? So I'm, to represent that, draw 180 on there, and then shade the area above. This is not a new question. This is an old question. This didn't say anything about the mean. We're just going to convert this to its z-score. I wanted to do an old one and compare it, to the sample means version. So let's convert this to its z-score. 180 minus 173.2 over 29.5. So we get a z-score of 0.23, which is not an unusual z-score. It's a positive value just above the mean. So it's like here. So this area should equal the area that's up above. Remember, the z table didn't work to the right, so use the complement here. Look up 0.23 in your z table. Let's see if I have a z table. Oh, look at that. I already have 0.23 highlighted. Cool. So the probability of being to the left of 0.23 is 0.5910. So that's 1 minus 0.5910. So we get 0.4090. There's a 41% chance if I randomly pick a guy on campus that they weigh over 180. Or I could say, maybe more interesting, 41% of BCIT male students are over 180 pounds. If you prefer to use Excel, this would be 1 minus norm.dist 180. 173.2 for the mean. Standard deviation is 29.5. And yes, it is cumulative. So that's old. I went kind of fast there. The new version is, suppose I randomly pick 36 male students from campus. What's the probability that their mean weight is greater than 180? So now I'm talking about X bar. So we're talking about the mean weight of 36 students. This thing, X bar, will be distributed normally. This little tilde is like shorthand in statistics. X bar is distributed normal. It will have a mean of 173.2. This is mu of X bar. And then the other, parameter is sigma X bar, which in this case is the 29.5 over the square root of 36. X bar is distributed normally with a mean of 173.2 and a standard deviation or standard error of 29.5 over root 36. Notice that's really the difference between this problem, part B and part A. So if we're drawing pictures here, we have the original population X with 173.2 in the middle. Then we have our X bars, which will also be normally distributed. I'm guaranteed that by the central limit theorem. One, because the population is normal to begin with. But even if I didn't know that, my X bar would be normally distributed because I took a large sample anyway. My sample size is 36. It will be a little narrower, like maybe I should draw it skinny. Because we know that the standard deviation is smaller for the means. So here's 180, and I'm looking for this area to the right. And then we'll convert that to a z-score and figure out what that is. What z-score goes with 180, and then we'll calculate that area. So to write this out, we want the probability that the mean is greater than 180. which is equal to the probability that, I guess I should have drawn that next to this one. How about I do that? And probability that the mean is greater than 180, which is the same as the probability that Z is greater than, and now we need to do the conversion. That's 180 minus 173.2 over sigma, which is 29.5, and the square root of n, which in this case we took a sample of 36. So in this case we're doing Z greater than 1.38. And I hadn't drawn it on my picture yet because I didn't know what it was. So then we get 1 minus the probability that Z is less than or equal to 1.38. You go to our Z table and look up 1.38, and you will find that it is 0.9138. So our answer is 0.0838. A big contrast in answers. If you're saying, what's the probability that one person is over 180? It's pretty high. Well, what are the chances that a whole group will have a mean over 180? Well, it's only 8%. So you can see that that happens because there's less variability. The results tend to be closer to the mean as n gets higher. So if I had studied 200 students, this would be even lower. You know, just you can, it would make the Z score. If you put 200 in for the square root here, it would make the Z score larger. And if you make the Z score larger, you end up with less area left in that upper tail. If you're an Excel person, you'd say 1 minus norm.dist, and then you'd input your parameters. You know, in this case, we're doing 180. Our mean is still 173.2. But here's the weird part. The standard deviation, we'll have to sort of, you know, rig it to work. It's 29.5 divided by the square root of 36. Like we can just put that in line right into the formula and then cumulative. I did do this in Excel already. You want to take a peek. Example 2 here. I'll post this document so you can see the difference between the formulas. Here's regular norm dist, and then now we're doing, for the mean, I had to sort of modify the standard deviation to be the standard deviation for the mean. So I kind of wrote it out up here. If you want the norm dist of x bar, just make sure you divide by square root of n. We'll do one more of these. We can use this to sort of make a decision now. My whole life, people have been telling me that body temperature is 37.0 degrees Celsius. I didn't know that the standard deviation was 0.62 degrees Celsius, but I guess it is. Body temperatures are probably normally distributed, but I don't really need to necessarily know that for my experiment here. I don't believe that it's 37. I feel like I'm usually lower than that. The only time I'm 37 is when I'm actually sick. So let's do a study. You know, I get 108 random people, measure their temperatures accurately. I have a whole list of 108 values. You know, here's my experiment. Then I calculate X bar, which is 36.4 for my group. And I didn't even bother with the standard deviation because I already know the standard deviation of the population. So is 36.4 close enough to 37 for me to say, yeah, it's probably 37? Or is 36.4 too far away from 37? And then I say, I don't think it's really 37. That's sort of what we're trying to answer here. One way we could do that is, determine the probability. They're saying it's 37, and we're assuming it's a bell curve. Now we're in to X bars. The middle would still be 37, and our value is 36.4. The question is, what are the chances of getting a result like this if we assume that it really is 37? Let's find the probability of getting 36.4. Well, we can't, but we can find the probability of getting 36.4 or stranger. And in that case, stranger meaning or further away from 37. So to be further away, I'd be going to the left here. Had my 108 people given me a result of 39, and I were in the upper tail, then I would go to the right. But because I'm below, I'm going to go to the left. Let's find the probability of getting a mean like this or smaller. I think I just said or, oh yeah, equal to or lower, but it doesn't matter because it's continuous. X bar will be distributed normal with a mean of 37 and a standard deviation of 0.62 over the square root of 108. Even if I didn't know the population, if this had been some weird, body temperatures look like that, say, I would still be okay to draw a bell curve here, maybe better than the one I've drawn, because my sample size is so big. My sample size is bigger than 30. So I'm really comfortable in doing this, even if body temperature is a weird distribution. It probably isn't. It's probably a nice bell curve. Let's calculate the z-score for this thing. 36.4 minus 37 over 0.62. Don't forget to divide by the square root of n. In some ways, I could have given you this formula for z-score at the beginning. Because even in a regular data set, if we're talking about individuals, your sample size would be 1, and the mean of any score would just be its score itself. This number turns out to be crazy, crazy small. It's -10. Remember how z-scores work, 1, 2, 3, and you pretty much have all the data. -1, -2, -3. And my z table only goes to 3 or -3, so I'm so far off the chart. My z table, the biggest value in there is 0.9990, at 3.09. So I don't know what this answer is, but I know that it's got to be smaller than, the smallest thing in my table. It's really small. We could get this in Excel. It's just norm.dist. Norm.dist, 36.4, 37. Our standard deviation is 0.62 divided by the square root of 108. And yes, it's cumulative. We go to our trusty Excel. I've already done it here for us. It's exactly what I just wrote out. The chances are, really, really, really small, just like we thought. It's 10 to the minus 24. So what does this mean? Everyone says body temperature is 37. We collect 108 people and get a mean of 36.4. The probability of that happening is so remote that one of two things has gone wrong. either my 108 people are the strangest people I ever could have picked. I picked the coldest 108 people on the planet, and that way they had such a weird mean. Uh, or maybe my sampling was just fine, and the original assumption of 37 degrees as being body temperature was incorrect. So this is evidence that the mean is not 37. We would say that this is statistically significant because this probability is so low. Generally, we use the threshold is if this probability is under 5%, we reject the null hypothesis. So our null hypothesis here was that the body temperature was 37. And we would reject that because this probability is unusual. It had a less than 5% chance of occurring. It had a 10 to the negative 24 chance of occurring. ten to the negative 24 approximately. It was like 4 times 10 to the minus 24, but really small. I said the central limit theorem needed a little tweaking. We're going to tweak it a little bit more. Here's a case where in many situations we don't know the standard deviation of the population that we're studying. We might know the mean, like we might have a good idea what the average result is, but the standard deviation is quite a bit harder. If that isn't known, then the central limit theorem, which relies on the standard deviation being known, needs to be tweaked a little bit. We would tend to approximate sigma with S. And if we're going to use S to approximate sigma, now we've introduced some error. And we know that S overestimates sigma, so things tend to be spread out more, which means that we need a new distribution. The Z distribution doesn't quite work. We'll use this new distribution called the T distribution. The picture that I've drawn here looks like the Z distribution. It has a bell shape as well. It has, a zero in the middle of the thing. It's symmetric, just like the Z distribution. The only thing is it's a bit more spread out. So the standard deviation for the T distribution is wider. Another thing about the T distribution is it's more flexible in that its shape will vary a little bit depending on the sample size. We said that if you take large samples, things tend to be not as spread out. But if you had to have small samples, then you have more variability, which means your data is more spread out. So we need a distribution that can handle those differences. But the nice thing about these t-scores is everything you know about z-scores pretty much applies to t-scores. They range typically from -3 to +3. Outside of that tends to be unusual. To calculate them and to read the table, we'll have to have multiple tables because each t-distribution is different depending on the sample size. I drew a couple of rough examples here. This dotted line here is your Z distribution, and the other two curves are T distributions. So you can see it's pretty similar. The difference between a Z distribution and T is pretty small. I said it depends on sample size. When n is equal to 2, like the smallest group you can have, then you have the innermost plot here. And you see it's quite a bit more spread out. There's more area in the tails. When n equals 4, you're already up to this part of the curve. And this is to scale, actually. So as n gets larger, the t distribution just becomes the z distribution. And you can see even by 4, they look pretty close. By 30, they're almost the same. Another reason for 30 being the magical number. When will we use this? We're going to use this t-distribution if we don't know sigma. And then in order to use it, we'll have to check some other things. We either need the population to be normal, or we need to have large enough samples. So if n is greater than 30, we're good to go use our t-distribution. If n is less than 30, though, then we have to have a population that's normal to begin with. Which means there's one case we don't know how to do. If sigma is unknown and n is small, under 30, and the population is not normal, then we don't know what to do. There are techniques. They're not super reliable, but there are techniques developed for that situation because it does occur sometimes. But we don't cover them in this course. So when we run into this situation, we just won't do it. We'll conclude we don't have the methods to accomplish this. To read the t-table, we'll need to convert from our original x values or our original x bar values and convert them to t-scores. And the formula is, very familiar. When we were doing z-scores, we did x bar minus mu sigma over root n. For t, we're just replacing sigma with s. So it's pretty easy. It's familiar formula and familiar math. The t-distribution is generic. We use it for more than just this situation. So as a result, we've come up with this terminology called degrees of freedom, where we're going to use the table, instead of using it in row n, we'll use it in row n minus 1 for this. Again, it's just a small tweak on, we're trying to get the central limit theorem to work even when we don't quite match all the conditions to use it. Here's an example, a little bit of a description of degrees of freedom. I have a class of 35 students. The score on quiz 1 was 72. I know the mean, but then I lost one of the students' papers. Well, if I know 34 of the papers and I know the mean, technically I can throw one student out. So I only need n minus 1 students in order to accomplish anything. So that's sort of an argument for why we use n minus 1. Sometimes we use degrees of freedom of n minus 2 or n minus 6. It depends on the application and how we're using the t-distribution. But so the table is generic. We just have to know what the degrees of freedom are for our specific application. And in this, for us right now, they're n minus 1. Here's your t-table. It's a table that works sort of backwards from the z table. It gives us area to the right. I'll do a quick example here. Suppose we have n equals 10. In that case, degrees of freedom will be n minus 1 or 9. When you're looking at this table, we go to our column for degrees of freedom, and we're in row 9. And these values in the table aren't probabilities, they're actually t-scores. And the probabilities are up on the top. So if I'm to draw a little picture here, suppose I have the number 2.821. I'd probably mark that up here, pretty far away from the mean. And then the area to the right of that is given in the table up above. We often call this alpha. I know we have had alpha in a few different things now, is in the Weibull distribution stuff too. and the exponential distribution, but here's a new alpha. It just means probability. So our area in the right tail is 0.01 in this case. So now that we can read that thing, well, I guess we can use, if we're in Excel, it's t.dist dot right, and it'll give you the area to the right of 2.821. And you have to tell it how many degrees of freedom. If there's also a t.dist function, so we could get the same equation by going t.dist of 1 minus 2.8219. And I think we have to say, for some reason they want us to say cumulative when we do it to the left, and we don't have to use cumulative when we go to the right. But these two equations should yield the same probability of, it won't be exactly 0.01, it'll just be close to that. Because it's more precise than the table. You look at the table for a second, you notice that these values are all between 0 and 3-ish. Some of them bump into 4s. For really small sample sizes, that's when you start seeing some crazy t-scores, 5, 7, 10. But usually, you interpret your t-scores like you do z-scores. It's just in those really small sample size cases where you get t-scores that can be quite a bit bigger. Like we never had a z-score of 7, but here we have a t-score of 7. But that's, looking at samples of size 4, which are, quite a bit of variation in a sample that's that small. A little example here. NAMZOR properties, they claim that their offices have an average sound transmission class rating of 52. They have a mean rating of 52. I don't think there are units on that. You're negotiating a lease for them, and you want to rent out some space, and you don't believe that they're as quiet as they say. You think that they're saying it's better than it actually is. To test the claim, you get the keys to 11 offices, and you go and measure the sound transmission class, however that is done. Office number 703 had a sound transmission class rating of 50. Office number 1808 had a rating of 47, and et cetera and so on. You went to 11 offices. So if you find the mean and standard deviation of these 11 values, you get these numbers. Use Excel to get those summary stats. Now, we think that they're wrong. Like, we think that it's actually under 52. And our data initially looks that way. The mean of our 11 was 50, which is smaller than 52. But is it enough smaller? So let's test this out by finding the probability of getting this result. What's the probability of getting a mean under 50 if we're to assume that they're correct? That the actual mean of the population is 52. Are sample means normally distributed? Well, I don't know yet. We should ask ourselves a bigger question first. Do we know the population standard deviation? And the answer is no, it wasn't given. Sigma is unknown. They told us that the population was normal. That's good to know. N is small. Like, we were really lazy. We only went to 11 offices. It's under 30. So we would be in trouble This is the case that we might not know how to do if they hadn't told us that the population is normal. Our x bar follows a t-distribution with n-1 degrees of freedom. Luckily, they told us that. Otherwise, we couldn't do it. Convert this thing to its z-score and let's solve it. I guess not z-score, it's t-score. So we want the probability that t is under. So convert 50. So 50 minus mu for the population is 52. Sigma for the population is unknown, so we're going to replace it with the s. So we'll have 3 divided by the square root of 11. T is x bar minus mu s over root n. We get our t-score. We get our t-score of 2.21, negative 2.21. Draw this out. Here's a t-distribution. Negative 2.2 is down here somewhere. And we want the area to the left of 2.21, negative 2.21. The table, I don't even have a negative table, so I'm going to just flip it over and find the area to the right of positive 2.21. Notice I didn't have to do 1 minus there because it's just symmetric. And now we just need to find this area using our t-table. So let's go back to that t-table and figure this out. I'll erase all this scribble here. In our example now, we have a df equal to 10, right? Our sample size was 11. So now we're in this row, and we're looking for 2.21. It's not there. It's pretty close to this one. It's between these two. If I were to draw this out, the area to the left of 2.228 is in the table. This area is 0.025. Or if I use the other number, the 1.812, the area to the right of that is in the table 5%. The number that we're trying to solve for is, pretty close to this one. Let's not interpolate. Let's say, what was our number? 2.21. I don't know what this area is because my table just doesn't give it. It's not, the table's too coarse. But I know that the answer is somewhere between 0.025 and 0.05. And maybe that's enough. Of course, Excel could get this. We just go t.dist .right 2.21 and 10 degrees of freedom, and it'll give us the answer more precisely. It'll be a lot closer to 0.025, right? 2.21 is pretty close to 2.228. So I'd expect this answer to be, roughly, even smaller than 3%, 0.026 or something. So yeah, we can finish this then. This area here, we said was between 0.25 and 0.5. So that's our answer. Our probability, the probability of getting a mean sound transmission class of, under 50 is somewhere between 2.5% and 5%, which is unusual. It's low. It's not as crazy low as the other one, where we had 10 to the minus 24. It's under 5% though. So this means that we have statistical significance. A rare event happened when we assumed that the mean was 52. So either our data was weird, we went to, the 11 worst offices, or maybe their 52 is wrong. So this is a case where I could use that in negotiations now. When I'm negotiating my lease agreement, I might say, well, you got to come down on the price a bit because your offices aren't living up to your claim, and therefore you set your claim to be the price based on a rating of 52. I think it's less, so maybe we can work out a deal. Of course, I might be wrong. Remember, I only studied 11 offices, so I don't want to exactly accuse them of being complete liars, but I would say that the data tends to disagree with their claim. If you're interested in sound transmission class rating, there's a little directory here explaining what that means. That's pretty much it for this unit. The next unit and the next few units rely on this whole idea of using probability to make a decision. So if you understood what we were talking about with low probability events, meaning you may disagree with a claim, then you're going to be in good shape moving forward, because that's the fundamental basis of the topic of hypothesis testing, which is what we're doing in the next few units. So I think that's enough for today. Hope you all have a good day, and I will see you next time.